Hello everyone. So today we will start this session. So let me introduce, since this is the first class, so let me introduce myself. My name is Anu. I'm a PMRF scholar at IIT Hyderabad, and I will be teaching you applied linear algebra for AIML. So basically, my intention is to create. Let me first make this meeting open to all. Just give me a second. Internet is also very slow. Why it is like this? So let everyone, host management, let everyone meeting access open. So I kept this as open.
Hello, ma'am. This is Nikita.
Yeah, Nikita, tell me.
Ma'am, actually, in the announcement of that portal, I just saw that there was a class yesterday, and I couldn't attend that. And what was there
Okay.
basically?
Yeah, sure. Okay, I will tell you the structure that we follow. Okay. So basically, for this particular course, we two TAs are assigned. So one is another person and myself. So you can join any of the TA class, and yeah, trust me, it will be very helpful if to understand how to solve a particular problem. But yeah, if you anytime mix the class, then also you can join through the live sessions recordings. So you can ask the NPTEL team to give you live sessions recording. Since this session is also recorded, so you people don't have to worry about it. So don't worry if you even if you miss the class. So our work is to teach you how to solve the particular problem and how to approach a problem or what are the basic concepts. So basically, in every week, you will have the video lectures to watch. For example, in the week 5, we had 5 video lectures. If you have went through that, then in that 5 video lectures, you will have to solve the problems related to it. Week 1 problem. Then after that, if you have any problem, if you have any doubt, if you have any issue related to problem solving or something, then two problem solving sessions are arranged by the NPTEL team. So the two sessions, like 1 week, in 1 week, two sessions for you guys. So if you are free to join any class, so it's okay, Nikita, you can join. You can see after that also, because that will be recorded. It's a compulsion for us. So that YouTube link will come. You have to check. If you want, I'll tell you who's that person.
Okay, ma'am. Sure. Yeah. Thank you.
Yeah. So sorry for the wasting your initial 10 minutes. Like, I feel the 10 minutes is very important. Actually, I had some problem in my tablet. I couldn't show through the tablet. So that's why I gave you this particular link for today's class. From the next class onwards, we will follow that link only that is posted in the NPTEL website that through it you got. So yeah. Uh, 1 second, I will just check. Okay. Tisha Rai or some, I don't know, I admit all. So hello, you have to join the Google Meet link. So please join the Google Meet link. Sorry for the inconvenience. I will again send in the chat box. You please join the Google Meet link, and I'm just ending this link. Okay, so in the first week, applied linear algebra for AIML. So what is the motive of this class or this course? Why you want to learn this class, this particular course? So I just want some brief introduction, because I just want to have a very interactive session so that we will not have any issue. Uh, Nikita, can you please start, like, from which background you are from? You are? Just a
So
one
I'm
line
doing,
introduction. Yeah.
yeah, I'm doing my CSE BE degree. I'm in first sem right now.
Okay. Very great. Okay. You are in first sem and you are learning from NPTEL. Nice. Yeah. Uh, Murthy Gupta, can you tell me about you? Just one line introduction. BTech, BE, anything. Okay. Sneha went. Anuraga Sam. Anuraga? Yeah.
I'm doing my PhD,
Oh, nice, nice, nice. PhD from where?
Government Engineering College, Patan Hill.
Okay, okay, very great. Then B in Bharti. Hi, ma'am, my mic was a problem. No, okay, okay, B graduate. I'll fix it. Nine, nine, nine. No issue, no issue. Moti, BM. Okay. So I don't know whether other students will be able to join the class or not, but yeah, we will start the class and I will upload the recording from this particular part so that we will not have any issue. Okay. So in this particular week, the professor taught about the solving. So I have not created my own slides because it was of no use because anyway we have to go through this one. So the total live session hour is 2 hours, and in the first hour I will teach you some concepts, and in the second hour I will go through the questions. That is very important. So I will go through the similar questions that is given in the assignment, but in not exactly same. So you please get to know that not exactly same questions we are going through, but yeah, similar questions are objective. Then concepts. First of all, concepts. First hour and then second hour. Okay. And I really want our class to be very interactive, to be very honest, because we are putting our efforts and you also giving your precious time. So please don't let the time to go waste. Okay, so since this was the first class, so that's why I gave this much introduction. So yeah, moving ahead. Actually, in the first of all, why we take this particular subject? This particular subject is very important because if you see uh, AI. Now people are talking about AI, and you all must be aware of the Chat GPT also. This is the Chat GPT built on the fundamentals of AI, that is large language model. So every model that we see, that we perceive in that we use nowadays, that is only AI model. Okay, so AI also have ML plus deep learning, DL. So these concepts you, and if you go into the depth, then these concepts are made of probability plus linear algebra plus little part of coding. So people often get confused, like we for learning AI we have to just learn the coding. No, it's actually mathematics. Okay, so it's a branch of statistics plus mathematics, we can say, and it comes under the domain of interdisciplinary. So it's okay, it doesn't matter from which background you are, you can learn at any stage, at any age. The only thing that you require is your learning willingness, whether you want to learn or not. So yeah, so this particular subject that you guys are learning and that you have enrolled, it's basically talking about the linear algebra, and we will be seeing what are some their application in the AI. Like the professor also introduced some part like the recommendation systems or wherever AI is used with the help of linear algebra. So that's why the course name is Applied Linear Algebra in AIML. Okay, and if you have seen the background, then you must have observed that this particular subject is from the Department of Mathematics, IIT Kharagpur. Okay, so moving ahead, one more and last thing that I'm giving is many of us enrolled in many of the courses. Like you must have enrolled in many other courses also. But after 1, 2, 3 week, we do all those assignments and everything. But after third week, we generally don't feel that we have to continue, and that's why we drop. So I just don't want, please don't drop the course. And if even if you don't understand anything, that's why these particular live sessions are there where we will have the interactive live sessions face to face. There you can see us, there you can ask us, you can mail us, anything you can do. So don't feel demotivated at any point of time, because these courses are designed by IIT professors, so that might feel difficult to use at some point of time. So it's okay, but anyway, whatever the level of difficulty will be there in the course. But one thing you remember, that all the assignments are very easy to solve, so that you will easily get the certificate, and that will be very helpful for your some placement things, or whatever you want to pursue, any research or anything. So yeah, so that was enough for the motivation. And one more thing, I'll be giving you my YouTube channel, because all these lectures will be uploaded there only. And yeah, that like Nikita asked. So one another person is taking this live session like yesterday happened. So that particular video is also uploaded in his or her YouTube channel. So you have to ask in the next class, then you can ask. Anyway, this was the first week video, first week, so it won't matter. So I'm just giving you my YouTube channel link. It's it doesn't matter whether you subscribe or not, but yeah, you can whenever you want to go through the lecture, then you can go through by clicking here, because anyway I have to upload as a part of my duty. So I'm giving you uh okay, so I have given you in the text box, or I am also giving my email ID. And these things I will not repeat in another class, because this is only required for the first class. Dot. Okay. Yeah. So yeah, in the first week, the professor taught these three things. We will be going with one of the examples. Okay. First of all, solving systems of linear equations. Then he taught something about the optimization, and then eigenvalue. So actually, this was the course content, total course content. Ma'am, at the end of the session, could you brief us about your research and background? Yeah, sure, sure. I'll brief. Yeah, Moti. Hmm. So yeah, so first of all, any number, suppose you have numbers in 2D, 3D or 4D, that can be represented as a form of vector space. So that here the term of vector space comes into picture. That is where we will be seeing vectors and matrices. Okay, so suppose we have two-dimensional vector. So two-dimensional vector means if we have x and y, and if you are representing any point, then how will you represent? Suppose you will represent 1, 2. So here you will write this is x1 and this is 2 is x2. x2 is equals to 2, x1 is equals to 1. Okay, so anything that ever it can be point in 2D, it can be point in 3D, we write it as a vector. So that's why also vector, you'll always remember vector is always a column vector. We are not considering as a row vector. There's also a reason behind it why we consider as a column vector. We will see when we are seeing it in the matrices. So this x is so that's why you can also write like x bar, or sometimes this is in bold. Okay, sometimes it's just in a bold, but yeah, this is not simple x. Don't consider this as a simple x. This x and this x is different. So it can be write as a simple bold. You can write it as x bar, or sometimes we write as a upper side bar. Okay, these are different notations. So x1, x2, it has two values. Similarly, y1, y2. So the main thing about the vector space, any vectors, set of vectors can be as a vector space when it follows closure under addition. So two properties, you always remember these two things. Closure under addition and closure under scalar multiplication. So for vector space, we have to follow these two properties. Two properties. I don't know whether you know about fields or not. What is fields? How will you define field? So yeah, this vector space, if you have any doubt or any of you know about anything, you can just uh, show the hand and you can tell. Actually, if it will be very better if you just speak out. I just don't know. And I don't know whether you have watched all those lectures of week 1 or not. Can like how many of you watched all those lectures? Like any 1, 2 lecture also? Like started doing it? 1, 2, 3, 4, 5. 5 members are there. Sorry, four. Out of four, how many of you watched 1, 2, 3 lectures? Any lectures? Okay. Nikita, how many lectures you have watched? Started with it. Okay, nice. Rajita, you? Okay. Only one is responding. P and Bharti. Bharti, can you please respond? How many lectures you have watched? Oh, nice. Then can you tell me what is field? It's okay. I don't care whether you are telling right or not. If you say anything, that will be very grateful for me. Okay, I just want to know like how much you understood. It's okay. Did you find it very easy, very difficult, or what? Can you just rate it 1, 2, 3 out of 5? 5 is means very difficult. 1 means easy. 2 means little difficult like that. Can you rate? Bharti, I'm waiting for a response. Okay, she is not responding. Anuraga, can you please respond? How many lectures you have watched? 3. Okay, that is great that you have responded. Yeah, so for the first time viewer, like if you are started with studying, then it will be around 3. She is very right. So, okay. So, any vector space. So, what I am trying to tell, if you are feeling that all the video lectures are in the rate of 3, then you please don't quit anytime. Like we generally, if you go we go to till the last and then we don't continue. So this is not the way one should follow. So 3 is very good that you are finding it. Okay. Then yeah, so every vector space is defined over a fields. So vector space is actually a function, or you can say mapping from field to vector. This is vector space. So yeah, so vector space is defined over fields. What is fields? So you always remember, example of field is R. Okay, here there are some properties. I'll tell you 1, 2, 3, 4. If you have any number, suppose 1, 2, 3, 4, 5, any real line number, and if you sum it, x1, suppose x1, x2 belongs to R, then will x1 plus x2 belongs to R? It is a question. Yes. So this is the first property. Then if 0 is a part of field, then by adding any value of x belonging to R will also leads to x. That is additive identity. That is additive identity. So first is closure under addition. So what we like when I was studying, then I used to get confused between fields and vector space. So fields is nothing, just you remember one thing, R, set of real numbers. Or there are other examples also, like set of complex rational numbers, set of complex numbers. And in many books you will find the set is like this, like this. Okay, this capital with little subscript is a set. Okay. So additive identity. Similarly, if you multiply by 1 to any number, it will give you simple same, means the one is a multiplicative identity. So this is following multiplicative identity. Okay, then what is the fourth property? The fourth property states that if you have any scalar like multiplication, alpha beta belonging to this one, then it should be commutative property. So this is commutative property. I'm telling you about the fields. Vector space is different thing. Okay, first let's understand field. Then if you have any associated property alpha beta gamma, then it is equals to alpha beta then gamma. Okay, similarly same applies for alpha plus beta plus gamma, then it will be equals to alpha plus beta plus gamma. Okay, this is associative property. Okay, so this is field, and I have given you example as Q, C and R. And one thing, your homework is for the next class, you have to prove, you have to whether Z is what? Set of integers is field or not. You have to tell. And if yes or no, if yes or no, whatever it is, explain why, explain how. So I'm making note of it. This will be your homework for the next class. Okay, coming back to vector space. So in the lecture, sir did not talk about the field properties of field, but in order to understand the vector space, it is defining our field. So that's why I make you understand what is field. And here in the whole lectures, sir is considering the field is nothing but vector space. This real numbers set always. So it is defined over R V to V. Okay. So what is this? I told you about the two properties. First property and second property about vector space. First property states that it is closure under addition. So if any vector v1, v2 belongs to V, this implies v1 plus v2 should also belongs to V. Okay, first property. Okay. And second property states if any alpha belongs to F. F here is what? This implies alpha belongs to R. This means that alpha and if here if and v1 belongs to capital V. This is capital V. Don't get confused between small and capital V. Sorry. This is capital V. Capital V. Okay. Notation is very important. Then this implies alpha into v1 should also belongs to capital V. Why I am more focused into capital and small? For example, let's say, I don't know whether you know about the Fourier transform or not, but yeah. For example, you are telling this capital X is a function of f of x. Then definitely this capital X and small f is different. Okay. So this is what it means is this capital V is a set of all the vectors or all the values, you can say. For example, this x1 is one of the vector that belongs to. So this is V. So this is x, y. Okay. So this belongs to here. Then x plus y should also belongs to V. Similarly, if alpha is belongs to some R, then alpha x should also belongs to V. So this is one more thing. Then whenever we add two vectors, then it will be component wise vector addition. But component wise means the x component will be sum to x component of another vector also, and y component will also be sum to y component of other vector. That we can see from the graph also. I know it will be very basic for some students, but yeah, we will start from basics to advanced. Don't worry, that will not stick to basics only. Okay. So for example, you have 1, 2. So you have to find this one. So this particular vector is this vector, okay, and this particular vector is this vector. So what is their sum? This vector. So you have to state whether this vector is belonging to particular vector space or not. Okay, so this is one of the property. So yeah, again going to the SIR notes, vector space, it is a set of vectors. Field, any field, field can be real numbers or set of complex numbers. Two operations, vector addition plus scalar multiplication, closure under vector addition, close under vector addition, and close under scalar multiplication. Closure property states that for all xy belongs to V, x plus y should also belongs to V. For all alpha belongs to R, this or x belongs to V, then x alpha is also belongs to V. So what it means that this also means this commutative. Similarly, associative. If zero vector for or there exists, this symbol means there exists a zero vector in V such that x plus 0 is equals to 0 plus x is equals to x. This is additive identity. Here it is coming from this particular things only, and this is coming from the property of fields. Okay, additive identity. And there exists y for every x such that this will be 0. Means if you have x in vector v, then you should have minus x also in vector v, so that x plus minus x should be equals to 0. It means that. Okay. Then fifth property states that for all x belongs to v. What is this? I don't know. For all x belongs to v, this x is equals to x. Okay. For all alpha beta belongs to r, x belongs to v, this means that this is associative property. Again, commutative and associative property. Then we will see with the help of example. Okay. First example states that if we have r square, tell me whether it is vector space or not. How will you identify? R square, so often we get confused what is R square. So I'm telling you R square is nothing but 2D plane. 2D plane. In 2D plane, this x-axis consists of all the real numbers and y-axis also consists of all the real numbers. That's why we call this R square. It means that it will consist of these infinite many points, because R is also infinite set. Okay, so this is component wise addition. If you see, this is following, and that's why this is also belongs to, because we will have anyway 1 2 3 4, so 4 6 also belongs to R, definitely, because R square is a infinite space. Again, alpha x is also, and also for identify the additive identity, 0 0 also belongs to R, because 0 belongs to R and 0 belongs to R. Okay. Because of the commutative and associative addition in R, vector addition is also commutative and associative. Similarly, R3, R power 4 will also be vector space. Okay. Now, R power n is also vector space. N can be any number, any natural number. Now, if you want to define the matrices, how will you define? You have to define like R cross n cross n. Okay. So we'll see that this is for matrices. So anyway, don't worry. I will upload this particular PDF in the link that you have provided, that you will get from the NPTEL portal. Okay. So moving ahead to the matrices. Yeah. This is matrices. So what it means? It is belonging to R power m cross n. This means that this row value as well as column values all belongs to R. And also this number of row values, don't get confused between m or n. The number of rows is nothing but m. Number of rows. The number of columns is n. Okay, so we have to find component wise addition. Now, since this is one of the element, don't get confused that this will be a element. No, this particular matrix, one matrix is one of the element of this particular set. So this particular set is a set of all the matrices of size m cross n. Now this particular matrix belongs to A, belongs to this particular set. So we have to check A plus B. Suppose B is also belongs to R cross M cross N. So whether it belongs to R cross M cross N or not. So in order to find A plus B, you have to find A11 plus B11, then A21 plus B21. Like it will be component wise addition. Similarly, if you multiply by alpha, then it will be multiplied by every element of the A or B. So that will also belong to this particular matrix. Then also this is also a vector space. Very good example of vector space is R square, R power n, or any matrices that is having R. Why we are considering R? Because it is defined over field, and R is one of the example of field. That's why we are considering R. Now let us say another example. Collection or set of the all polynomials in X. Suppose with real coefficients. So this coefficients we are defining as a field. It is defining over field. Okay. So that the field. That's why we are. I told you what is field. So if you plus any two element belongs to this particular set, then that will also belongs to P of n, Pn of r, because that is again a real number. That will, if you sum two real number, and then again it will get this two real number, and it will also in the form of polynomial. So then also it will belongs to that particular polynomial. So it is also one of the example of vector space. One more thing, that what are the two properties? Closure and addition, and scalar multiplication. Along with this, you also have to check whether 0, 0 is belonging to that particular vector space or not, because you have to also satisfy additive identity. Again, whether if 0, 0 is belonging to that one, then again minus a or minus any particular vector is belong to that particular set or not. If you identify four properties, then you can say it is a vector space. Now, till now, we have seen all the possible vector spaces. Okay. Now, we will see what cannot be the vector space. Okay. Let's see. Examples of vector space, we have seen this. Okay. Let's see what cannot be the vector space. What cannot be the vector space? Suppose you have a plane. Okay. Now we define R square. Okay. Sir, have not done, I am telling you. So this is R square. Let us say R square minus particular area. This will give you one plane in 2D. Will it be a vector space or not? I'm just asking. Suppose these two values, if you sum this particular value plus this particular value, it can be leads to this particular value, right? Can be lead to this particular value, and this particular value doesn't belongs to this particular plane, then definitely this is not the example of vector space. So this particular thing we call it as a affine combination of line, or also we can affine combination, not line, affine combination. So we will see also this, and this is very important in apply linear this AIML, that we define a hyperplane. For example, you have two sets, red and this is blue. Okay. Now you want to find a classification. For example, will have new set. What is AI? It predicts the what is the possibility of new data. For example, I have one thing, that the price of this particular pen, I don't know whether you will say able to see this pen or not. Okay, the price of this particular pen is 2 rupees, and price of another pen is 3 rupees. Then you have to find a new pen. Suppose this is another pen that is a new. Then you have to predict what will be the price of this particular pen. Then using the AI, you will find it will fall into which category, first pen or second pen. For example, it falls into the first pen category. Then you will predict, the AI will give you answer as 2 rupees. And if it falls into the next category, the AI will give you the answer of 3 rupees. This is the simplest example that every machine learning engineer starts with. Okay, so then in order to separate two data, you will find the hyperplane in mathematics. Then you have to find, how will you find? Using vector space only. So that this is one of the example of that. Okay, moving ahead. We saw vector space examples also vector. Now, one other term comes into the picture, subspace. What is this subspace? This is also very important. So we will see. Okay. Suppose you have uh, an image. So I suppose if you have image. Okay. So every image, okay, this image, suppose this is this particular person. Okay. So this particular image is made of pixels. And these pixels have values from 0 to 255. So suppose if you have very dark value, then dark value will have the value around 0 something. Then if you have very light, then it will have value around 255, highest value. Then according to the intensity, you are giving the value. And why I'm telling, I'll tell you what is the basic of it. Then this particular, suppose this is 0, this is 1, this is 2, this is 4, this is 140, this is something, something, this is value, and this is also will have some value, this will also have some value. Then how will you map it? Then you generally map into a vector. This particular row will go here, then this particular row will go here, then this particular row will go here, and so on. So this makes this as a vector space. And in practice, you will have abundant of data that any machine learning model needs to train it. So we generally store an image in the form of a vector to train any particular AI model to give you a fruitful output. Okay, so this is a grayscale image. It will have the pixels uh, m cross n. Okay, intensity values are associated in the form of either it can be form of 0 to 1 or 0 to 255, depends on the grayscale or RGB values. So RGB is red, green, blue. Okay, so Emily's handwritten data is also in the form of, it is very one of the popular data set in Kaggle. So people used to train to check if suppose any small student is there, small child is there, then if he's learning, how will you first of all you will show this is 0, this is 1, this is 2, this is 3, then again you will suddenly give 9 value, 9 image, 9 digit image, then he will identify this is 9 correctly or not. So he has to identify whether it is 9 or not. So in that way we also give data data to the model, any model in the form of either in the image or in the form of anything. So MNIST data digit 0, 1, these are the data sets of the MNIST where it is given in the form of image, and in that the intensity values are stored in the form of a matrices or vector. Generally we store in the form of vector like this. Okay. So feature vectors. So also the feature vector is also very important. For example, you have to identify which feature you want to incorporate. For example, a house is there. Then the house have also area. It has the perimeter. It has the price. It has a location. So for example, you are not much concerned about the number of rooms in the house. So that is not a feature. That will not comes into a feature. So you have to remove it. Some features were very important that will create a feature vector, theta 1, theta 2 to theta n. On the basis of that, we will train and will try to find this theta 1, theta n by using in the machine learning. Okay. So now we will come back to the vector space. So a subset, you have identified what is vector space. Now what is vector subspace? So it will again a subspace, then any W that belongs to V. This is vector space. and it follows all the properties of vector space, then it is a subspace. It should also be a subset of V. The difference between subset and the vector space is only it should be a subset of V. So yeah, if it is subset of V, then it will be subspace. And again, what are the two properties of vector space? Closure under vector addition and closure under scalar multiplication. With with one property extra is, with two property extra is, and additive inverse should be there, with 0, 0 should be there, and negative of x is also be there. So that you will have x plus minus x is equals to 0. Okay, that is only existence of 0 and existence of additive inverse. Okay, additive inverse is x minus x. So what is additive inverse of x is minus x. This is inverse, and additive, this is additive identity. I am repeating some things very often just so that you'll not remember any time in the future. And it is also a possibility that you can miss the you may prefer not to watch the lecture also, because anyway I'm going through all the concept that the professor taught. Okay, so if and only if, so W is a subspace of V, which is a vector space, if and only if W is a closed under these two properties as the same as a vector space. For example, let's see. This is one of the line. This line is falling through origin. Means it have 0, 0. Means first property verified. Which is verified? Additive identity. 0, 0 is there. Then if this particular value is there, the negative is also there. Okay. Second property also are verified. Then if x1, x2 and y1, y2 is there, then their value is also there. Because this is infinite line. Okay. Then is also a vector space. X1 plus x2 is equals to 0. This is the line. This is the line that follows through, that is going through origin. Or you can also say x plus y is equals to 0. So this is also falling. Or else you can also verify by seeing this. If x1 plus x1, x2 belongs to and y1 belongs to w, then x1 plus x2 should be 0 and y1 plus y2 should be 0. Right? Then that what implies this particular is also 0, then also belongs to W. This you should know how to do this particular thing. What we are trying to do. First of all, we are checking any first vector. This is V1. This is V2. Let's say V1, V2 belongs to W. Then we have to prove whether V1, V2 belongs to belongs to W or not. Then how we will check? If V1 belongs to W, then it means that x1 plus x2 is equals to 0. This implies this. And if V2 belongs to W, then this means that y1 plus y2 is equals to 0. And if you sum it, then we will get this particular thing. This particular is x component, this particular is y component. This is also belongs to this. This means V1 plus V2 belongs to W. I hope this clears. So this additive and closure property is verified. Similarly, if you take any parameters as alpha, this is also belongs to alpha for all alpha belongs to R. So this is also closure under scalar multiplication. So any line passing through origin is a subspace of R. For example, any line doesn't pass through origin. Suppose x plus y is equals to 1. Now let us this is one of the subspace. This is also one of the subspace of R2. Okay. No, so this is also one of the, suppose this is K. K means K is a set where what? X1, X2. Such that X1 plus X2 is equals to 1. Now tell me whether this is a subspace or not. This is a set. K is a set where K is subset of V. This is following. Okay. Now tell whether K is a subspace or not. Just let me know. Here x1 plus x2 is equals to 1. And if yes, how? If no, how? Any response? Waiting for 1 minute.
Ma'am, it's not a subspace. I
Okay.
mean, it is not a vector space
Okay.
because if you consider another y1, y2 as a vector belonging to K, which follows y1 plus y2 equal to 1, and if you add them, it's not closed under addition because it will end up becoming 2.
Yeah, yeah, very true, very true. So as Nikita explained, this is one of the set that is what is that belongs to V. Sorry, that is what is the meaning of that? Again. But yeah, this is not a vector, a subspace. This is not a subspace because if it is not closure addition, and also zero doesn't exist. So you can check zero is existing or not. Okay, one of the basic thing. Okay, nice. So that's what Sir has also explained. This is not a closed under vector addition and scalar multiplication as well. Also, zero doesn't belong to this. So now let us see this particular circle. Now you tell me whether this is a subspace or not. You have, what is this meaning? This is a circle. All these points are there inside the circle such that x1 plus x2 square is less than 1. Whether it is a subspace or not. So one thing I'm telling you, subset. So yeah, for a subspace, for a subspace, you should have, if you define this as a W, W should be a subset of vector space. Vector space, what we know? This is R square. Again, it is a subset of vector space. That is satisfying. Now we have to check whether the other properties are satisfying or not. So again, this is not closed under addition. This is not closed under addition because if you have taken any two, this one, if you sum it, it cannot be. It is not sure that whether it is necessary it will be less than or equals to 1 or not. It can be not equals to 1, less than or equals to 1. So yeah, again it will not. It is not closed under addition. But yeah, it is having additive identity. Okay. So one thing we have to, it is a subset. So I was not able to recognize this particular symbol. This was a subset. Okay. So same thing. This is not close under scalar multiplication. This is not subset. Again, it will not close under scalar multiplication. If you take any alpha, alpha belongs to R. This is R is field. So this alpha x belongs to R. This is not a this particular thing. And also, if you take close at this addition or let us see with one example. Suppose we have 1, 2, and we have 3, 4. So 1 square plus 2 square. Again, we have to take it properly so that it should be less than or equals to 1. 0.5 or 0.75 or zero point 0.6 or zero point 0.8. You just check as a homework whether it is close under addition or not. So these two is giving, if you sum it, this is W1 is equals to this one W2. Then you have to check whether W1, W2 belongs to capital W or not. Then only it will be close under addition or not. This is one of the homework. Okay, because this is why I'm telling, because sometimes yeah, one property is fine, but also sometimes we get to know whether it is following other property or not. Okay, so by default this 0 0 is always a vector space or trivial space. That is also called trivial subspace. Similarly, V is equals to R square is also always a trivial subspace. Similarly, this particular singleton 0 is also trivial subspace, or any line passing through the origin is subspace. Similarly, any hyperplane passing through origin is also one of the example of trivial subspace. Passing through origin only is very important because we have to make sure it is following additive identity and additive inverse. Now, one question arises. Are these the only subspaces of R square? Are these the only subspaces of R square? Yes or no? Definitely no, right? Because R is infinite set. You can have many subspaces. or you can have only restricted to this particular subspace.
Ma'am, I think only these subspaces, because we have just shown that if we have seen that if line doesn't pass through origin, it is not a subspace. So, like the subspaces would be line and the origin
Yeah,
and the trivial subspace.
yeah. So just take one example. If you have R1, R2, R3, till Rn as a vector space, is this finite? No, right? Then how can you have a finite number of subspaces? For example, R square is not a itself finite. Okay, this Rn, n is like you cannot measure till what value of n. So in that way, it is not like these are the only subspaces. But yeah, if you have particular subset, for example, R square, this particular line, if you have y is equals to x, y is equals to alpha x, y is equals to beta x, it can be like this, right? It can be like this, 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 it can be like this. But yeah, this again, like you're told, these are the only lines that is all passing through origin. But in that passing through origin also we will have many lines. Okay, so in that way it is infinite. But yeah, this is very true if you consider line passing through origin, then this zero singleton and this r square, then this zero value, we are the only subspaces. Then in that way it is true. Okay, so we defined vector subspace. Result W is a subspace if and only if it is following this thing. Examples of subspace of R we also defined. Next thing, subspaces we have seen. Similarly, this will also goes for 3D. I'll not get into it. Okay. This is a plane. This is a plane equation passing through the origin. I hope you understand. This is what alpha x plus beta y plus gamma z is equals to 0. This is the equation of plane. So this is a subspace closure addition, and the only thing is it should not be 0 simultaneously. Okay, what if it is 0 simultaneously? Will it be a subplane then? Will it be a plane or not? If it is 0 and simultaneously, if you try to draw, if you draw, is there any case if it is passing through origin and then all alpha, beta, gamma are 0? This can be case where one of the gamma or alpha beta is 0. This can be case when one of the alpha beta gamma is 0. But there is nowhere case when alpha beta gamma all are 0. Only possible when you will have 0 0 0. Think about it. Why we are constrained to this particular property? Homework 3. I'm noting it down. We will discuss so that we will have any question. The first question what I gave, some question I gave. I'm noting it down. So think about it, like why we are constrained to this particular thing. Okay. So moving ahead, v is equals to r cube. Then if you have this particular uh, w, then you have to check whether it is a subspace or not. How will you check? Suppose v1 belongs to v, w, this is capital W only. v2 belongs to capital W. This implies v1 plus v2 should also belongs to w. So let us t1, t2. Okay. So since t is any function of r, so this is also belongs to w. So this is closure addition. And since t is also belongs to w, t belongs to r, the r it consists of 0 also. So 0 0 0 is also there. Additive identity and additive inverse is also there. Fine. And if it can be any alpha, beta, gamma, not all 0. Again, we are considering only not all 0. What is the reason for this? Why we are considering only non-zero? The reason is, I'm telling you, the plain equation is x by alpha is equals to y by alpha is equals to z by alpha, sorry, beta, z by gamma. So if it all becomes zero, then it will be becoming indefinite. That's why we are not considering it. Anyway, x is equals to y is equals to z is equals to 0 is existing. It doesn't mean that alpha equals to beta equals to gamma equals to 0. It doesn't mean. It is not necessary. That's why. Okay. So examples of trivial subspace, again in R3 also it is the same, planes passing through origin, lines passing through origin. Then again R3 is the only subspaces. Yes, for particular R3. Okay, set of matrices we find it is a subspace, vector space. This is also, yeah, one more thing. The set of all symmetric matrices is also, so what is symmetric matrix? Symmetric matrix is A transpose is equals to A. Similarly, A transpose is equals to minus A transpose is anti-symmetric matrices. These are also subspace. Tell me how. Just like, let us try to take how. So you have W is equals to W is a subspace such that A transpose equals to A. Okay. Set of all matrices A such that A transpose equals to A. And this is a subset of Rm cross n. Okay. This A is a matrix. Okay. How it is a subspace? This is subspace I am telling you. So let us say V belongs to W, U belongs to W. So this implies V transpose equals to V. This implies U transpose equals to U. Now let us sum V plus U. Will it be belongs to W? Yes or no? Since this is equals to V transpose plus U transpose, and here V is made of all M cross N. So the transpose will also belongs to our M cross M. So yeah, this is also a subspace. It is closure under addition. And since V and U also have 0 values. Okay, A also have 0 values. And if it is A 0 value, means this is 0 0 0 0. Definitely it is a symmetric matrix. Then it is following additive identity. Additive inverse, similarly additive inverse. Okay. So we have to check like this. Similarly, anti-symmetric matrix is also a vector space. But if we consider this particular thing, we cannot tell this is a vector space. This is a subspace. Why subspace? Because it is a subset of another vector space that is biggest. This one is biggest, right? This is the biggest in Rm cross n. So if any matrix, particular type of matrix belong to that particular vector space, then that will be a subspace because it's a subset of that. Okay, I hope you understand. So now we will close here subspace, vector space and all. We will move to the linear combination of vectors. Also, one of the thing, diagonal matrix is also subspace. And anti-symmetric matrix also subspace. Anti-symmetric matrix also follow these things, right? Okay, what is linear combination of vectors? Now I will tell you one very important property, which is linear independence. Yeah, Nikita, tell me.
No, actually, I have a doubt. I don't know if it's like very silly, but
Yeah,
you
sure.
just said like when you have a subspace, like vector subspace, like it can't be a vector space. So basically, now you can tell any vector to be like almost similar to a column matrix or a row matrix. Then can you tell that R n can be like a vector subspace of R m cross n or something?
Okay, you are telling made the column vector.
Yeah, column vector is like almost similar to a column matrix.
Yeah. So for example, what is column vector? Column vector is M1, right?
Yeah,
And
yeah.
this row vector is 1 cross n. So in that in this column vector, you will have column is equals to 1, and in row vector you will have number of row is equals to 1 that you can write, and definitely it is following under set of matrices. So it is a subspace.
No. My question was when you take Rn, just a vector,
Rn.
like you just, yeah. So this is a vector space, right? So
Yeah.
can you tell this is a subspace of, n cross n cross 1 or something like that?
Oh, no. Why we cannot tell that? You have to understand this is one dimensional and this is two dimensional.
Oh, yeah, got it.
You cannot compare these two, right? For
Yeah,
that you will have should have the values in both rows and columns. Here you are not considering that. Suppose you
okay,
will
okay.
suppose let's say with this, let's understand with one of the example. Suppose you are having a particular type of vectors that have particular property. Okay. For example,
Mm.
what we saw x1, x2, it has a property x plus x2 is equals to 0, right? We saw this. Suppose this is W, this is this set. This is one of the particular type of vector that is having this particular property. And that this particular vector, if we plot, we are calling it as a line. Then this particular subset, this W. W is definitely a subset of what V. V is R square, R2.
Yeah,
Then definitely it is a subspace. Then we cannot compare this with respect to Rm cross n, right? This is not a
yes,
subset of
yes,
that.
yes.
This should also follow, right?
Yeah,
Uh,
yeah, got it.
yeah, okay. It's okay. I feel very proud that uh, one of you asked question, because anyway we are spending time to understand the concept, and it is very important, Nikita, since you are in first year. So it's very good that you have started with this particular thing. Okay, so another concept is linear combination of vectors. So we have
Excuse
yeah,
me,
yeah,
ma'am.
Moti, yeah, tell.
Ma'am, before moving ahead, I just wanted to ask, like, does this vector space and subspace thing comes in computer vision? Like, we have images
Yeah.
H
It
cross
comes to the
W
computer
cross
vision.
C thing.
Tell me.
So, what would be a subspace? Like, we are dealing with cats and dogs images. Will cat images be a subspace and dogs images be a subspace? Like, what would be the analogy in that domain?
Okay, so yeah, so as you know, the R square or R power n. Okay, as I told about the image that we write it as a vector. Okay, v1, v2, x1, x2 till xn. This is one particular column. Okay, then one particular column, then this particular thing, this particular thing. So row wise, we are emitting it as one column vector. In practice, we generally do this. If you want, I'll tell you with Python example also. But yeah, in practice, we generally do this. Then we have to check whether this is a subspace or not. This has to follow particular properties of subspace, then only it will be a subspace. Otherwise, it is not a subspace. And why we consider only this vector space or subspace? Because it follows a particular properties, and on top of it, certain rules are built up. Okay, that's where we are considering these things. Otherwise, it is not necessary that it will be a subspace. Any particular image, if you are writing in the form of vector, then it is not necessary it will be a subspace or vector space. We have to check whether it is following a subspace or vector space or not. I hope this clear.
Okay, ma'am. Yes, ma'am. Thank you,
Yeah,
ma'am.
we will see. Slowly, we will see that. Okay, before moving to the next topic, time is 7:30. Yeah. So actually, the next concept is linear combination of vectors. Okay. From there, we will see what is span of vectors, then what is a linear span of vectors, and what is linear independence, and then what is the basis of the vectors, basis of the matrix, basis of the vectors, or basis of the particular coordinate system. For example, in practice, you often have incurred with the I, J, K. These are the unit vectors. This we call as a basis. Okay, so this I, J, K, if it is you are writing in the form of 2D, the I you can also write. Sorry, this is 3D, then it definitely is a 3G. So 1, 0, 0, this is I. This is 0, 1, 0, this is J. This is 0, 0, 1. So these are the basis vectors. So using these vectors, you can define any other vector. Through the linear combination of these three vectors, you can define any other vector in 3D plane, R cube. So here we will come with the topic of linear independence. So what we do, if any two vectors, for example, let's say any two vectors v1, v2 belonging to R square, because any vector will belongs to R square if it is defined over the field of R, then if it is, then you have to consider linear combination, means alpha v1 plus beta v2 is a linear combination. This alpha v1 plus beta v2, where alpha beta are any scalars, then this particular alpha v1 plus beta v2 is a linear span of two vectors, which is v1 and v2. Then again we have to check whether these two vectors are linearly independent or not. So in order to follow whether these vectors will be a basis of vectors, basis or not for any coordinate system, we have to check whether they are linearly independent or not. Now we come across this particular topic. Okay. So any vectors and scalars, this particular thing. The vector W alpha 1 v1 plus alpha 2 v2, this particular thing is called linear combination of the vectors. And if you plot this span, this is called linear span. Span of v1, v2 till vn. You can see with one of the example. If v1, v2 belongs to this alpha 1, alpha 2, then v1 plus v2, if you plot all those values, then it will be linear span by v1 and v2. So consider the set S is equals to v1, v2 to vn. Vk belongs to R power n. Then this is linear span as I told. And if this is this all are 0, alpha 1, alpha 2, alpha 3, then it will be a line. This is one of the proof that this linear span is always a subspace. If you plot this alpha 1 v1 plus alpha 2 v2 such that this is belongs to R, this linear space is always a subspace of R power k. K can be 1, 2, 3, 4, 2, 3, 4, 5, like that. Okay. Now linear independence. So I'll rush now. These are some in the last lecture, last or second last lecture of first week. Sir only taught about the proof of it. So proof we will see, like analytical also we can see. But yeah, I'll teach you what is linear independence or not. How we'll check whether it is linear independent or not. Because that is from that the questions are there in quiz 1. So okay. Suppose you have vector v1, v2 till vn belongs to R power n, and alpha 1, alpha 2 to alpha n belongs to R. Then, as we know, alpha 1 v1 plus alpha 2 v2, so on, alpha n vn is a linear span. Okay, and this is always a vector space, a subspace. Then, the linear independence property states that this particular linear span is equal to alpha 1 v1 plus alpha 2 v2, so on, alpha n vn is equals to 0. Here you just note that if and only if alpha 1 equals to alpha 2 equals to so on alpha n is 0. So if this particular thing follows, then these set of vectors are linearly independent. For example, we saw I, J, K. So if you sum it, you will have 1 0 0 0 1 0 0 0 1. If you sum it, alpha 1 0 0 plus beta 0 1 0 plus gamma 0 0 1 is equals to, you will have three equations, right? Alpha plus 0 plus 0 is equals to 0. Then 0 plus beta plus 0 is equals to 0. Okay. Then if you equate it to 0, means alpha v1 plus beta v2 plus gamma v3, if you are equating to 0, then 0 0 plus gamma is equals to 0. This implies alpha is equals to beta is equals to gamma is equals to 0. So it means that these three vectors are linearly independent. Means if it is equals to 0, if and only if alpha equals to beta is equals to 0, gamma is equals to 0. So this is the meaning of linear independence, and opposite is for linear independence. So that's what Sir taught about linear dependence and linear independence in the last lectures. And one of the vectors in S can be written as a linear combination of the remaining vectors if they are linearly dependent. Now, in this example, we cannot write one vector in the form of other two vectors, some linear combination or something. So that's why these are linearly independent. And if there are some linearly independent vectors, then you can take this as a basis for particular dimension. So, for example, if you have 3D R3, then you cannot say that the only basis exists is this particular thing IJK. You can have multiple basis, any three vectors, that is linear independence can be a basis. Okay, that spans the whole R3, because their linear combination will be any of the vector belongs to R3 that will span the whole R3. Then it will be linear independence. Now, the only concepts till now are linear independence, vector space, subspace that I covered. And yeah, and then also linear independence. So if a particular set of vectors are linearly dependent, so one vector can be written in the form of the linear combination of other vectors. So this is the meaning of linear dependent. So from here, the concept of rank of a matrix comes into the picture. That is not covered in the week one. I hope it will be covered in the upcoming weeks. So yeah, till then, this is a linear independence property. So also one of the properties, any linearly independent collection of vectors can have at most n vectors. Okay, at most one vector it should have. It cannot be having more than n vectors. Definitely you can follow it from the linear combination of vectors. So if any collection of n plus one vector will always be linear independent. These are some properties. If you add any vector over it, then it will make it a linear independent. For example, if you add any other fourth vector in ijk vector, unit vectors, then it will be definitely causing it as linear dependent. These are the properties. Yeah, and you please watch last lecture that he taught about the sum of the proofs that we are not going through. The proofs are very general. Uh, yeah, if you understand that basis, as I told, what are the bases? If they are linearly independent vectors, then it will call the basis of Rn, also called basis vector. So any vector, why this is basis? Because any vector belonging to R power n can be uniquely expressed as a linear combination of these basis vectors. So also there will be proof how it will go by the contradiction. If it is not written, then we will prove whether it is written or not. So they are having some proofs. That's the only thing. Yeah. So I covered whatever taught in the first week. Now we will go through some of the questions. Why I have taken solution, I don't know. So yeah, please guess what is the answer. Let P is a subspace of R power n. Which of the following statements is or are correct? So if it is a P of subspace, then we know that it will be following associative property. So this is correct. And it is following multiplicative scalar, closer under multiplication, multiplicative scalar, closer under scalar multiplication. Sorry. This is also for closer under addition. So all of these, so answer is D. Very straightforward. Okay. Yeah. Which of the following statements are true? Tell. Tell me the answer in the chat box. The first option is any superset of the linearly dependent vectors is linearly dependent. What is superset? Any subset. Superset means adding any vector. Any subset of linearly dependent vector is linearly dependent. Which of the following statement is or are true? Means 2 or 3 options may be correct. 2 or 4. C. Okay. Any subset of the linearly dependent vector is linearly dependent. Any superset of the linearly dependent vector is linearly independent. Can you explain the analogy? How it is, Bharti? One and three. So yeah, A, B, C, D. You will have 1 and 3, both 2 and 4, only 1, only second. Yeah, I know the answer. Who told of 2 and 4? Tell me the analogy how 2 and 4, Bharti. So yeah, uh, one thing I'll just let you know. Before going to the answer, we should have the ability to think. It's okay whether it is wrong or true, right? It doesn't matter. I was also like you. No, ma'am, it is C. Okay, Nikita. Nikita, you told. Nikita, you told no. 1 and 3.
Yes, ma'am.
Yeah. So you are right. The answer is 1 and 3. Nikita, can you please tell me how you thought this is 1 and 3?
So ma'am, basically, superset of linearly dependent vectors. So when you take a set of linearly dependent, it'll come out to be like alpha xi plus, I mean alpha 1, alpha I xi, summation of that,
Yeah, yeah.
it'll be 0. And then any superset of that is, I mean, logically if you think it tends to follow the same thing because,
Yeah, yeah. So first is very straightforward. Linearly dependent means any other vector can be written as a linear combination of other vectors present in the set. Okay, present in the vector. For example, v1, v2, v3. So what is linearly dependent? I'll tell you. For example, 1, 2, 2, 4, 3, 5. So you can say this 2, second vector is nothing but a 2 of v1. Okay, so if you to say only 2, this is represented in the form of other vectors. So if you take any superset also, it will be linearly dependent because other vector can be written as a as in terms of a other vectors present in the particular subsets. So this is very straightforward. The third thing was very tricky. How you can tell any non-empty subset of the linearly independent vectors is linearly independent. Yeah, Nikita, can you tell some words?
ma'am, basically what I thought was in linearly independent thing, it tends out not to be 0 in like all the cases except one where all scalars tend to be 0. So like there can be a possibility when you cut down some of the terms, like when you take a subset, it might.
Okay, Okay. Okay. Yeah, so analogy one thing we can see that it linearly independent states that alpha 1 v1 plus alpha 2 v2 plus alpha n vn is equals to 0 if and only f alpha 1 alpha 2 alpha 3 all are 0. So for example, if you take two vectors out, for example, let's say if you want to check anything, just see with this example 1 0 0 0 1 0. You can verify anytime. If you are getting doubt, it's okay, but you can verify with one other example. If you verify with example, it will be true always. So 0 0 1. So if you take only these two, these are linearly independent obviously, because at one time only one thing is 0, right? If we are making it as a 0, this alpha and beta, so alpha plus 0 is equal to 0, 0 plus beta is equal to 0, and 0 plus 0 is equal to 0. So if it is making it as a sum equals to 0, then this implies that alpha is equal to beta is equal to 0. So third also true, first also true. So answer is C, both first and third. Okay, so moving ahead. Alright, this answer was physical. Yeah. Tell me whether the subset is linearly dependent, linearly independent, or basis, none of this. You have to just identify whether these subset are linearly dependent or independent. A, linearly dependent. So you can say linearly dependent. You have to solve system of linear equation. Simply, the answer is very simple. Here you will have two values in column and three values in row. If you solve 4 alpha plus 2 alpha beta, okay, I'll tell this is what wide matrix. Okay, wide matrix. Wide matrix always have infinitely many solutions. I don't know whether you know or not, but wide matrix, how it is wide matrix, let us see. 4 alpha plus 2 beta plus minus 8 gamma is equal to 0. Then 18 alpha plus minus 4 beta plus 6 gamma is equal to 0. So you can see you will have the number of variables more than the number of equations. Then definitely you can assume any other variable. So if you can assume any other variable, you will have an abundant number of solutions. Then in that case, definitely it will be linearly dependent. So any vector can be represented as the sum of the linear combination of any other two vectors. Because anyway, one value you are assuming it, any value. So you cannot find the solution. So you can always assume any other vector, any value, alpha, beta, gamma as many other values, any value, infinite values. So definitely infinite many solutions, then it will case of linear independent. I think answer A. So correct. Yeah. Now tell which is the answer. Which of the following subsets of R3 are subspaces? I want answer from all. P.N. Bharti and Anuraga, Sam, Moti, Nikita is always telling. P.N. Bharti also told. Anuraga, Moti also told. Anuraga, I also want answer from you. All of you, please tell. I just want interactive session. Just think whatever we have learned. A. A are subspaces. A and D. A and D. A and D. Do you think these Moti A and D, P and Bharti A? So A is a common answer. Only D. Though D is occurs, sorry, a coefficient is like it. Okay. Yeah. because if alpha is negative, then it will not be the case. Thank God. So answer is A. You are very correct. Nice. So yeah, this is one of the plane alpha 1 x1 plus c is x2 minus x3 is equals to 0. So it will have the additive identity, additive inverse also, and it will follow. Second, it will not follow the additive closure identity, uh, either in the form of multiplicative, scalar multiplication and additive. And third, also it will not follow because it can be negative and positive also. It is not necessarily. And third, yeah, D as Moti told, a coefficient is negative. Nice, very nice. So next question. Yeah, now you think and then. So if you think like this, no, I'm very sure that you will get definitely more than 80% in your final exam. Anyway, we will be discussing the problems related to your assignment problems. So don't worry about that. uh, Assignment problems you will definitely solve, and in the final exam also you will be solve you'll solve definitely 80% of the problem. So yeah, next is fifth question. Take your time, think and tell. D D B. Bharti is telling B. Okay, so how you have solved, Moti?
Ma'am, actually, like if you look the first span, we are thinking 1, 3, and 2, 0. You'll see that we want to get 4 minus 6. So the second thing, vector 2, 0 can't give us minus 6. So the thing would be minus 2, and minus 6. And if we add uh, anything like uh, no, actually, I made a
Anyway,
mistake
you have
here.
to just
Sorry.
check the linear combination of these vectors will be belong to that one also, no? Or not. If any linear
Yeah,
combination is leading to that particular vector or not. If it is yes, then the span. Otherwise, no.
yeah. 3, 2 will definitely not belong because you can see that 2 and 6 and minus 3 and minus 3 are actually linearly dependent. They are just multiples of each other constant scalars. So 3, 2 is
Yeah.
not a that. So I made a mistake here. It could belong. So the right answer would be B, actually.
Okay. Right answer is B. No, B. 3, 2 is belonging to that, right? 3,
3 to won't
3,
belong,
2. Okay, okay. Yeah,
but
yeah.
4,
3 and 2. Yeah, it will not belong. Because 2 minus 1 is 3. 6 minus 1 plus 9. No, 3 to won't belong. So yeah, you'll have again have B and D, right?
yes, ma'am.
So can you check between B and D?
The answer would be B because we could find a multiple minus 2 and let's say 3.
Yeah, answer is D.
Minus
Answer is D.
D.
Because 4 and minus 6 also will not belong. How? Why? If you plus 2, if you multiply first vector by 2, then it should be 2, 4 and 6. Negative will not come.
Ma'am, if we multiply 1, 3 with minus 2, it would be minus 2 and minus 6. And the second vector by 3. It would be 6 and 0. The sum would be 4 and minus 6.
Yeah, okay. It will be 2. So answer is
Uh,
B. It is what? 1 plus 4. This is minus 6 is no. It's belonging to 4 and minus 6. How it is 4 and minus 6 is belong?
ma'am, if
Wait.
the alpha would be
2 minus, yeah, tell me. Minus 4.
alpha would be minus 2 and the beta would be 3.
Alpha would be,
Minus 2
beta would be,
and
beta would be.
3.
Okay, yeah, so we don't have to check like this. We have to just, you can solve the problem, no? Alpha plus 2 beta. 2 beta is equals to 4 and 3 alpha is equals to minus 6. So alpha is equals to minus 3, and then if you put it here, minus 3 plus 2 beta is equals to 4, and this is 7 plus 7 divided by 2. So yeah, it is giving up a unique answer, right? For a unique alpha beta, you are getting this one. So this is solvable. Anyway, whatever value you are getting, this is solvable, so answer is B. But if you try to find this one, uh, alpha plus 2 beta is equals to 4, 3 alpha is equals to minus 6, alpha is equals to minus 2, minus 2 plus 2 beta is equals to 4, this is 6, 2 beta is equals to beta is equals to 3. Yeah, actually linear combination means it should not be a negative point values. Answer should be D. I don't know why B is given. I was also guessing it.
Ma'am, no, B is right. I mean,
X, 1 second.
Combination, we are taking alpha
So
to
B
be
is right only,
equal.
ma'am.
B is right. How it is right?
Yes, we can write it as a linear combination of that one, ma'am.
But I am doing correctly only, right?
Is it?
Alpha plus 2 beta is
Yes, the value is correct only. Alpha is minus 2, gamma is beta is 3 is the right only.
alpha. Acha.
Then we can write.
Okay. So yeah, this particular value you should get. So D is not correct. So this particular value you should get. It should not be in fraction. So it should not be in fraction. The value you should get. So this is belonging to this one and this is not belonging to this one. This is not belonging. Anyway, any value is not leading to this one. So like this you have to solve.
Ma'am,
Solve.
but when we define the linear combination, we took the alphas from the real number. So the real number could include fractional.
True. Sorry for the confusion. Yeah. Real number can be 0.5 also. Point any value also. I think span it is checking the linear independence or any combination, linear combination. I have to check. Just wait a second. What exactly span means here? Span of vectors. Set of all linear combination. Yeah, so it is correct only according to definition that set of all linear combination of vectors. So if any set of all linear combination of vector is also giving 4 minus 6, then D should also be the answer. There were some typos, like these are the last year assignments. So I think D.
ma'am, just a doubt, like, why is it D? I didn't get you.
Okay, D. Okay, if it is belonging, then it should not belong, right? Yeah, okay. This is not correct. Okay, this is again not correct. Okay. I was just guessing it is belonging to. Okay, if it is not belonging to, then yeah, A. Can you check A? So you have checked that this is not belonging. So yeah. Okay. So visually I was getting confused. So B is the only answer because this is one of the linear combination of these two vectors. This is not a linear combination in these two vectors. This is not belonging to. So yeah, the answer is B. So yeah, alpha beta can be any value in the set of R. And span means it should belong to a linear combination of vectors. So okay, going to the next question. Hmm. Tell me this answer. So the question is, let 2PQ be a subspaces. Okay, which of the following is true? P plus Q is a subspace. P intersection Q is not a subspace. P union Q is not a subspace. Only true you have to find. So now obviously answer is P plus Q is a subspace because if you take any if P is one of the element of another subspace, then Q is another element of another subspace, then it should be closer under addition, closer under scalar multiplication, and uh, this additive identity and additive inverse. I think answer should be A. Yeah, answer is A. So moving to the next question. Yes. Tell me this answer. I'm waiting for your answer. B. Linearly independent. Okay, very great. Again, you have to find alpha plus alpha v1 plus beta v2 like that. Okay. And regarding the next class, I'm not sure whether I'll take through Teams or Gmeet. I will update the link there because I was having some problem while presenting the screen in the tablet. So yeah, actually I was getting message from other students. So sorry, some of the students might not join class today. So yes, answer is B. Next question is, and if you want to understand a particular question, I will tell with the pen and paper. Actually, we first saw the basics and everything. That then we are moving to the questions. So I feel that it is not required. If any of you find it is difficult to solve or if difficult to find, I'll tell you with the pen paper also. So don't worry, don't hesitate in asking that. So then only I'll move to the next question. So yeah, one thing is that one more thing. Any matrices can be written as v1, v2, v3 like that. This one is column vector, column vector, column vector. So one column vector c1, c2, c3. So like that. Now you tell me which of the following matrices have linearly dependent columns. I just want to solve it properly. You just have to follow the linear combination. Take your time. At least one. I will also take time to solve. 2-3 minutes will be required. Okay, B. Nikita told. I'm waiting for Moti answer or Bharti answer. Moti also told. Moti, Nikita. Okay. So both of you told B. Let us see whether the answer is B or not. So answer is B. Very correct. Bharti, okay. It's okay to do mistakes. You can just cross check. If you have any problem in solving it, just let me know. You have to just check whether where is the pen? Whether it is following linear combination of vectors or not, like alpha, beta, alpha v1 plus beta v2 plus here C1, C2, C3. So alpha C1 plus beta C2 plus gamma C3 is equals to 0 if and only if and only if alpha equals to beta equals to 0, gamma is equals to 0. So you have to just check. Suppose he will have three equations. Suppose let's since answer is B, so I'll solve B only. 2 alpha plus 2 beta plus gamma is equals to 0. Then 3 alpha plus beta plus gamma is equals to 0. Then 1 alpha plus 3 beta plus gamma is equals to 0. Then you have to solve and you have to check whether the solution is only alpha is equals to beta is equals to gamma is equals to 0 only. Then only it will be linearly independent. Okay, I hope you understand. So moving to the next question. Again, the similar type of questions come. Is or are correct? This is the second last question, then we will end the class today. So okay, I am very confident that you guys will be able to solve this because we have covered the basics of everything. So yeah, it may take time. You have to just check whether these tools are linearly independent or not. If it is not, then only it will be a spam. So answer is D. All of the above are the answer, the correct options. Now you just let me know this one. Yeah, this question is very somewhat tricky, different. You just think which should not be a subspace of R, M, N. Mm, okay, so very correct. Like Nikita and Moti are almost correct in all the problems. So answer is determinant. That is very straightforward. The determinant you have to calculate using cofactor. Like it we have to calculate if you have taken any particular value, then you have to find the minor determinant, then again next value, then minor determinant like that. So it is it is not a subspace as we saw. So, so till then we have solved 10 questions as well as basics of vector spaces and subspaces. Then we saw properties of linear independence and which are not linear independence. Then we also saw super subset and subset of linear independent and linear independent. Please try to remember some of the properties from the problem stated here, and then yeah. So as you were asking about my qualification, I'm telling you. Um, yeah. So Moti was asking. So yeah, I am a direct PhD student. Like I have joined the PhD program after my BTech. I did my BTech in 2020 from a central university uh, in Chhattisgarh, and then I joined PhD in IIT Hyderabad. So I will be getting two degree, MTech and PhD both, in upcoming 4 or 5 years. It depends on the duration. So, and one more thing, like I joined in January 2021. Like after 6 months completion of my BTech, I joined in PhD program. That it is also called direct PhD. So after that, I got this PMRA fellowship. So under this PMRA fellowship, we are given a task of to teach the students. Either they can teach all the PMRs can teach through NPTEL online, or they can also go through the nearby schools or colleges to teach. So I prefer to teach through online since this is part of my fellowship. And moreover, I'm working in wireless V2X communication that works at the intersection of machine learning as well as signal processing and communication system. So I am from EC background. I hope this is clear. So I want to ask one thing, like anyone wants to pursue research in the future out of you?
Ma'am,
Thank you, ma'am, for the introduction. Yeah, sure, Nikita. Please go ahead.
Yeah, Moti. Do you want to pursue research in the future?
Yeah, yes, ma'am.
Okay. So what is your background? You're
Yes, I have just completed my BE in computer engineering from Thapar University, Patiala.
okay.
So,
So
yeah,
yeah, it's
I'm
a good
currently
opportunity to join after BTech. Don't wait for masters and then like then PhD.
yes, ma'am.
Yeah, you can join,
So,
and you can
okay,
also
ma'am.
apply for the PMRA fellowship. You might have aware of this thing. Huh?
Okay, ma'am. Yes, ma'am. I'll check about
Yeah,
it.
since you are a computer science student, then like you can work in the intersection of AI, ML, and that networks also. In my college, there are many people who are working in networks, wireless networks, or anything that if find interest to you. So, okay, Nikita is a first year BTech student. What do you aim to become?
actually, I'm very clueless in what to do, but yeah, I want to pursue research, but like I just realize it's very unpredictable. I don't know what I'll end up doing after 4 years. So
Yeah. Yeah. So, yeah, since you are BTech first year, you just don't worry about anything. So, what is your branch, Nikita?
CSE.
CSE. Okay. Yeah, so
I'm studying in RV College, Bangalore.
Bangalore. Okay. Nice. So nice to know about you. I don't know. There will be many students who wanted to join the class. I think they missed it just because of this Google Meet and this conversion. So anyway, I will be posting this recording to my YouTube channel, and I've also shared the channel link. And I just want you to continue the class till the end. And happy learning. Thank you so much for joining the session.
Ma'am, just a
Yeah.
second.
Yeah,
Just can you scroll up to the ninth question?
Yeah.
The ninth.
Yeah.
So in this, basically, you have to check for any number of alpha betas, the sum, I mean, the linear,
Yeah, for
wait,
example, if
the
you
linear
go with the first
combination.
option, then the linear combination of first span, this first thing, is equal to linear combination of this one. Obviously, this is 0, 0, 0. Okay, so this one is correct. Then again, if you go through this, the linear combination of this thing is equal to this. How you can tell? Because this vector v1 is actually multiplication of some linear dependent to this particular vector. And this particular vector is linearly dependent to this particular vector. This is a way to check, because these twos are linearly independent among themselves, but actually they are the same vector with respect to this particular thing. That's why this one is also correct. Similarly, this will also go through this, and this will also go through this. Basically, you have to check alpha v1 plus beta v2 is spanning to R2 or not. Means it is making to all the vectors or not. If it is yes, then definitely all those will be equal.
No, no, no. My doubt was, I mean, obviously, if it's a span, then obviously it will belong to
Yeah, yeah.
R2. But when they're using equal to sign for two different vectors and the span of that, so when you do for some alpha beta, if you take a span of first one, I mean the linear combination, should it be like equal to the linear combination of the second
Yeah,
one?
it is linear combination only. It is not like alpha beta will be equal to both alpha beta. It is linear combination only.
So my doubt is like for the second one, 2 minus 3, 4, 1, 0, minus 2, suppose you take some alpha and beta here, and if you take the same alpha beta to the second thing, it won't be equal, right? The linear combination of both of
No, no,
them.
no, no. It is span. Lead alpha beta can be any value, right? Span means it is spanning the whole 2D. Means this is also spanning the whole 2D. This is also spanning the whole 2D. Then definitely this will be equal, right? Then only we can write equal.
Oh,
It is spanning the same thing. Means in other way we can say it is spanning the same thing. Then we can say it is equal.
okay, okay.
Yeah. Okay, it was very good question.
Ma'am,
Yeah, Moti.
yes, ma'am. Before you end the class, I just wanted to ask something. So, like you are working in signal processing
Yeah,
domain.
yeah.
So you must be. Do you like? I just wanted to understand the application of linear algebra in real life.
Okay.
So, you must be encountering some signals that are like the basis signals and whose linear combination gives other signals.
Ah,
So,
yes, yes, many times.
so like,
Yeah. So have
so
you seen the radar detecting the object? How it detects? It detects through reflected signal that it comes. So basically, it it checks with one signal with some addition, or that addition value you are only checking. If it is greater than particular value, then you would say that this object is detected. Or another way we can say this is correlation. Suppose you have two signals, x1 and x2. Then x1 correlation with x2, this is the actual correlation, is actually a vector operation. And any signal can be written as a vector. So this is x1 vector, x2 vector, x1 vector, x2 vector. Then you find it with, you compare with respect to a threshold, th. Then only you would say this particular thing is existing. This particular object is existing. So this is one of the example of vector apply linear algebra, or linear algebra you can say.
ma'am, do you encounter subspace-like structures like which are actually helpful in practice?
Yeah, subspaces are also there. Like I don't know whether you know about this subspaces as column space, row space, and null spaces. So this column space is nothing but the linear combination of all the columns of the matrix. Null space means linear combination of all of the vectors, that is all of the vectors of the column space that is leading to 0. So that is giving you the homogeneous solution. So in that way it is useful. So if you asked exactly the real life example, then we can say suppose in the in AI we are finding intersection of many hyperplanes. So for example, you have many classes and you have classified through many hyperplanes. Then you have to find the solution of these hyperplanes, right? So one hyperplane can be represented in the form of one equation. Other plane can be represented in the form of other equation. So you have to finally find the solution. So how will you find the solution? Through the null space. Null space. Null space is also one of the example of vector space. Null space is defined by Ax is equals to 0. So set of all x such that ax is equals to 0. Where a this will be 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the x1, x2, x3 is equals to 0. Where this x1 plus 2x2 plus x3, 3x3 is equals to 0 is one of the hyperplane, first hyperplane. Similarly, this will be giving second hyperplane. This will be giving third hyperplane. So the solution of this will be giving you through the null space only. So this is also one of the example of vector subspace.
Okay, ma'am. Thank you, ma'am. Thank you for your time.
Yeah. Sure. Okay. Thank you so much for joining. Okay, I will.
Ma'am, sorry to disturb you again, but
Yeah.
yeah, in the ninth question,
Huh.
now I got like the thing, and then for can you just scroll down
Yeah.
to the ninth? So 1 and 2 I understood.
Yeah.
Basically, how do you verify the third one is my question.
Okay. So let's calculate the span of this one, and then let's calculate the span of this one. First of all, you have to you don't verify like this. First of you check whether these two vectors are linearly independent or not. If these two vectors are linearly independent, then definitely these will be equal. Is this linearly independent? Obviously yes. If this is also
Oh, you basically check like whether those it is linearly dependent, and as long both of them are linearly dependent, or
independent.
they're
Huh. Yeah.
independent or
No.
dependent.
These two vectors are themselves are independent, but yeah, this will be dependent. But these two vectors are independent, oh. Then only we are calculating the span. Otherwise, how will you calculate the span? I'm telling independent of these two vectors. These, not these.
Ma'am, no, I'm confused now.
Okay. Yeah. Tell me.
No, how does it matter whether it's dependent or independent? Span is just like a combination of all of the, I mean, possible combinations, right?
Yeah, it can be possible combinations, but if you have to check whether these two, for example, if these two are linearly independent, then you have to check whether these two are also linearly independent or not. Then only you will be equal.
Okay.
Ma'am, maybe I could share my opinion on
Yeah.
this. Like Nikita, what I did was that quickly for the first thing, the first span thing, 2, -3 and 4, and 1, 0 and -2. If you subtract those, you'll obtain the second thing's first vector, and if you add those, you'll obtain the second thing's third vector. So these are essentially the linear combination of these two things. Therefore, their span must be the same. I mean, that was a quick reasoning of mine.
Yeah, correct. But basically, don't like when I also encountered for the first time, I was also getting confused. But then I saw whether their linear combination is also giving the one particular thing, or the another linear combination is also giving the one particular thing, then it can be equated.
So basically what was my thought was like when you just tell it is a subset, then you can like verify because I mean there are some things you can't tell like everything is you know what I mean, ma'am, like the fourth
Yeah.
one, you can tell subset easily
Yeah.
because you verify some cases and some might not be true, then it doesn't matter. But when you're telling equal to, everything should agree for both of them, right?
Yeah, you're telling about alpha beta values.
Yeah, exactly. For first one, it makes sense because it's zero.
Yeah.
Whatever be the value of gamma, it doesn't matter.
Yeah. In the second one also we can observe these are dependent vectors.
So basically, I didn't get the logic why it should be dependent or independent to be,
Yeah.
span to be
Let's
equal.
see with dependent or non independent. For example, you have alpha plus beta is equals to 0. Then this is 1. And second vector is 2 alpha plus 3 beta is equals to 0. This is one span, okay. Second span is alpha plus beta is equals to 0, 2. Okay. Then some 3 multiply with 3. 6 alpha plus 6 beta is equals to 0. So if you write this, how you can write? This is alpha plus beta equals to 0. You can write this 2, this is 4, 6, 3, 3, 9. This should be 9. Yeah. This should be 2 alpha plus 3 beta equals to 0. So basically this one and this one is same, right?
No, the thing is, why are you assuming it to be zero? Because
No,
linear,
no,
I mean,
I am
span doesn't
assuming this is
mean.
this is 1 1, this is one vector, this is 2 3, this is another vector, this is creating one span. Then I'm assuming dependent vectors. Suppose 2 2, this is dependent to this. Then we are assuming 2 3, this is 6 9, this is dependent to this. This second logic I was telling that things that this one is dependent to this one and this one is dependent to this one. So
Okay.
basically, if you try to solve, this will be the same, but the vectors are different. Okay, you can tell vectors
Okay.
are different, but anyway, the combinations are same.
Ma'am, actually, yeah, I just don't know how to tell what I'm like. I mean, I'm not able to express what is my thought. So I'll just work on it and be clearer in the next
Yeah, yeah,
class.
you
I'll get
ask
it
me in the next
clarified then.
class, okay. But I hope you
Yeah, sure.
understood why I'm taking the dependency.
Oh, yeah, yeah, got it.
Yeah. So
Yeah.
second option was from that. Third option I will check, like whether it is dependent or not. We will reach.
So basically,
Uh,
when two vectors you are given, and then when you're finding its span, and suppose the two vectors are dependent, then span should be
yeah,
equal.
it is
And
sure
suppose
here.
it is
Yeah, yeah.
independent, it can be or it
Yeah,
cannot
yeah,
be. Then
yeah.
how do
That
you
is
check
sure.
it?
It can be, it cannot be, yes. So if they are
Ma'am,
dependent, then
but
definitely their span is also equal.
ma'am, what is the question in the third part? Like, what's the issue?
Uh, we are trying to understand if they are not dependent, if they are not dependent, then whether their span will be equal or not.
They are not dependent. You're saying that the vectors in span 1 and vectors in span 2, these two vectors are not dependent. They are independent. Whether their span would then be equal. You are exploring
Yeah,
this.
yeah, yeah.
Okay. Okay. If they are
See, if they
independent,
are
I don't
dependent, we
think
can
it
see
would
from the
be.
equations. Now, if they are not
Yeah.
dependent, then we have to check. Let us see it.
Because if you have two vectors, it would span a plane, and if those vectors we cannot represent it in that form, I don't think they would represent exactly the same plane.
Beta is equal to 0. So here we are getting alpha beta equals to 0. Okay. Now let us see this one. Alpha plus 3 beta equals to 0. Minus 3 alpha minus 3 beta equals to 0. Plus alpha plus beta equals to 0. So what I'm getting? Alpha is
Ma'am, it will also end up being 0 0.
so okay. Yeah. So what I was telling, both are giving you alpha beta equals to 0. But yeah, only if I'm equating to 0. So means these are linearly independent. These two are linearly independent among themselves. Okay. Now if we equate it to some other values, let us say 1 or 2, then it is not necessary that alpha beta values for both will be equal. You're telling that now?
Yeah, basically now it's independent, both of them are. So how can you verify all the possibilities?
No, no, no.
I mean,
See,
that
one
can.
thing, yeah, one thing we can tell, if they are independent, okay, suppose 0 1 0 0 0 1 1 and this one was that now 0 1 0.
No, in this given third example only, both are independent, right? So,
Yeah, suppose these are three sets that are linearly independent. Now this is spanning to one R3. The span is same, no? If they are independent and they are spanning to all the columns, all the vectors in the R3 space, then these are also linearly independent. It will also span to all the columns, all the vectors in the R3 space. Then there they are spanning the same thing. R3. This one is also R3. Then definitely it will be same, right? In that sense, you think.
ma'am, like if you don't mind, can you give an example, like maybe in the next class, or like
Okay, okay,
if you
okay.
have now,
Yeah,
like two vector, I mean, span of size should be the same, but they are not, span should not be equal.
okay. Okay, I will explore this time in the next class. Okay, yeah, I will tell. Okay, we will see this example. Okay, so I'll quit the class. Thank you so much for joining.
And thank you, ma'am.
Thank you,
Yeah,
ma'am.
yeah.